Hi, I'm Gibran Yapur, and I'm going to be talking to you about icing machines. So we followed the Berkeley's paper on this subject matter and where we built our first prototype of an icing machine. Icing machines work on the fundamental principle of the icing model, here in which we can define the spins of each oscillator. The spins give us the direction of where the atom is spinning. So we can have either a positive spin 1 or a negative spin -1. And here you sum all that up and we can get the Hamiltonian of this function, which Hamiltonian would be the least amount, which would mean the most optimum route of this problem solving. You can see our icing machine on breadboard built by 4 oscillators in this breadboard circuit. These oscillators are coupled together by their respective potentiometers. These potentiometers are not only coupled adjacent oscillators but also crossing the oscillators. This ensures that we have an all-to-all connection between these systems, these oscillating systems. Now, if we zoom in a bit into one of the oscillators, we can see that they are built upon a capacitor and an inductor, which creates the resonance in this circuit, which makes it marginally unstable and makes the oscillation. These oscillations are not controlled at the start. They are not synchronized with each other. So for this, we need not only to tune the potentiometers to a necessary ratio, we also need to apply what is called a subharmonic injection. This function is double the natural frequency of the oscillations, and it would make all these oscillators settle with each other and synchronize, giving us a result of these 4 oscillators connected to each other. They are separated by pi phase or 90 degrees to each other. And this could differ depending on the situation or problem we want to fix, such as a max cut problem where we want to identify the optimal partitions for each one, or the traveling salesman problem where we want to find out the optimum route for each of the cities. This is then plotted in our Kuromato model, where we can find out how reliable these results are in relation to the Kuromato model, in which gives us the settling time of the settling phases of each of these oscillators in a probabilistic way, and we can see how reliable, like once again, the system is. Icing machines have a big future ahead of them since they can represent quantum computing in terms of phases between oscillators. So this is a practical aspect of how we can represent information between yes and no binary states and have more than one state between, as you can have many states between more than 0 and 90 degrees. There can be many phases in between. And that can give us more information, a more efficient way of storing and transferring data. This can not only be applied in such oscillators, but also optically by using the Ising model, and has a very promising future in all our computing needs and lives.